Now, you remember the original setup here was all about preschoolers, toilet stops, etc., and you already worked out part I and part II. And so the third part of this question was to explain which of the assumptions for Poisson would not be met in this situation. So what you have to remember here is, first of all, what are the assumptions for a Poisson distribution? So let's just list them out. First of all, the events must occur at random. Okay. The next one is each event or happening must be independent of one another. Independent. So that's one thing. The next one is the rate at which an event occurs must be constant, should be constant. Okay, so that's the third one. And there is a fourth one. Events cannot occur simultaneously. Cannot occur simultaneously. Right, so the question said, explain which of the assumptions for Poisson would not be met. So they're not actually asking you to say how could it be met. You need to say for what would it not be met. So it could be a case of eliminating some. So the first one, events must occur at random. Well, you could probably explain that would actually happen in this case. Each event should be independent. Well, I'm not quite sure that they are independent. So in this case here, I would say these events unlikely to be independent. Now, I've stated this particular clause, but now I've actually got to put it into context. So the context in this case would be something along the lines of, well, once you've been to the toilet, once been to toilet, you would think that it would be longer, or it would be longer before needing to go again. So there's an outside factor that's affecting the independence of this particular event. So yeah, that's one thing there. The rate at which an event occurs should be constant. See, this one, I also don't think the rate is not constant, because lots of different things can affect the rate of which the small child may need to go to the toilet. This could be how often they are eating, how often they are drinking, how often and how much, that's a much, and what they are drinking. Okay. And these are all outside factors. Yeah, I mean, and it could also be things like, are they doing exercise? Are they running around as most kids normally are? Can affect bladder control. And you'd also like to think that as age increases, child bladder control improves. So all this adds up to the rate not being constant. Okay. The final one, events cannot occur simultaneously. Well, that's correct. You can't go to the toilet twice at the same time. So that one and the random ones, they work, but it's the independent and the rate at which the event occurs should be constant. It doesn't. So the key point here is identify which one of these four, or two of these four, or whatever, will help this whole not be met, and then you've got to remember you've got to put it into context. Remember the context, okay? So, because if you don't put the context, you get no credit whatsoever. So yeah, try and make that. That's actually a merit question. That's an R. Right, on to the next question. So for this question here, it's Claire has decided that her own preschoolers' toilet trips or toilet stops on a 2-hour trip could be modelled well by a Poisson distribution with a lambda of 1.8. Use this information to predict the likelihood that she will have no more than one toilet stop to make in 3 of her next 5 1-hour trips. So that's interesting. So we've got 3 of the next 5 1-hour trips. So we're using a Poisson distribution here, and we've got a lambda of 1.8. Now it's important that a lambda equals 1.8 per 2 hours. So the first trick here is that we're only interested in 1-hour trips. Okay, so therefore the lambda for 1 hour is 0.9 per hour. So we've got to use that. Now the other thing is that no more than one toilet stop. So we need to find out what the probability using the Poisson distribution of no more than one toilet stop. So another way of writing that is that the probability of x is less than or equal to 1. Okay, so we can go onto our calculator and do this particular calculation. So if we look at the calculator here, the first thing, I'm on the stats screen and I'm going to press the execute button, press the distribution button, just go to the side, press Poisson. Because we're looking for x is greater than or less than 1, we can choose BCD. And we'll put x is equal to 1 because we're wanting to know no more than one toilet stop, and I've already put the lambda in there, 0.9. So we've got all our information in there, that's all that's required. So we end up with a probability of that equals 0.772, or round it up, 5. So that's the probability that there's one toilet stop. Then it says here, and this is interesting because this gives you a bit of a clue to what they're looking for. It says, identify and justify any other distribution used. Okay, and we get a little bit of a clue here, 3 of the next 5 stops. So that's set up nicely, if you realize it, for a binomial distribution. And the reason being is that we have these parameters that are available in that particular distribution. So we're going to use our information that we've got here from the Poisson. So we've got the probability of there being less than or equal to 1 toilet stop, and now we're going to work out that she will have no more than 1 toilet stop in 3 of her next 5 trips. So to do that, we need to go on to our calculator again, because we're going to find out what the probability of x is equal to 3 when there are 5 events with a probability of 0.7725, and we're going to use the binomial. Why? Well, remember the binomial distribution I think it's ideal here because our success is either she's going to the toilet or she's not. That's the binomial distribution, and this is the probability of her of no more than 1 toilet stop. It's all about going to the toilet stops. So let's go back onto the calculator and see what it tells us. So you can see on our calculator, we go from the stat mode on the main menu screen. We go into, whoops, I'll just get out of this. This is what, of course, it looks like when you're doing something opposite. So we go distributions, we're going to go binomial, and we're looking for BPD because we're looking for x is equal to 3. So we choose that. So x is equal to 3 because that's what we're wanting, only 3 out of the next 5. So there's 5 trials, and our probability, we'll put our Poisson distribution, probably 0.7725. We put that in there, and we come out with 0.238. So what that's telling us is that using the binomial distribution will give us a probability of 0.239, really. 239, that is the probability that Claire's daughter will have no more than one toilet stop in 3 out of the next 5 one-hour trips. So what does all this mean? I mean, it's asking, that we've identified and we've figured it out, we've worked it out, we've predicted the likelihood. Now what we have to say is, well, why? Well, binomial is like I said earlier, it's suitable because there are two options. Okay, either she goes to toilet or not. So that is the success or fail criteria. Now the other binomial factors, number of fixed trials. Yep, well we've got that. There are 5 in this case, 5 trials, because she was looking for 3 in her next 5 one-hour trips. We're talking about independence is the next thing. There's nothing that clearly indicates or not indicates independence apart from possibly what we answered in the previous question. So in this case here, we're going to assume independence. We haven't been asked to not agree to this, so we'll assume independence. And the other thing about binomial, of course, is that the probability of success, so the probability, I'll just get back a bit, the probability of success is the same. Okay, and so what you need to say there is that we're saying that using the binomial at 3 out of our 5 next stops is that there's no other factors that are going to affect that. Of course, it goes against what we said in the last question, but this is a separate question. We're trying a different distribution. We can make some assumptions in this particular case because we're trying to get it to work, not to work. And that's how you'd answer that particular question. This question is an excellent question, guys. If you'd done this first part, worked out the fact that your lambda had to be halved and worked out your probability of 0.7725, that gave you a U. If you then went along and used binomial and worked out this answer of 0.239, that was worth an R, and all of this extra explanation justifying it, and that's what the question has said, we want you to justify it, that gives you the T, which of course is your excellence.